What you have in front of you are two different types of circuits. We have something called a half adder. Over on this side, a full adder. But how are they actually different and what they're used for? Well, they're both used to support the calculation of binary digits. So, let's focus on the half adder first. If I was to do this, 0 add 0, we know the answer in binary is 0. 1 add 0, we know the answer is 1. 0 add 1, we know the answer is 1. 1 add 1, we know the answer is going to be 0 with a carry. I'm going to do carry 1. Nice and simple. So let's trace it through this circuit in itself. If A is 0 and B is 0, we have 0 going to be here and a 0 going to be here. And we know we've got a 0 here, and we know we're going to have a 0 here, we have a 0 here, and a 0 here. On this NOR gate, 0 NOR 0 will give us a 1, which is fine. On this gate here, it will give us a 1, and on this gate here, it will give us a 1. 1 NOR 1 will give us a 0. So we have a 0 which will travel here, and a 0 which will go down here. 1 NOR 0 will give us also a 0. So what we have is x being the carry and y being the sum. So if we were to do another one, we know that 1 add 0 gives you 1. We know that. So the sum should be 1 by the end of it, and the carry should be 0. So we trace this through, we're going to have 0 here, we can have 1 here. 1 or 0 gives you 0. We're going to have this 0 here going here, which gives us a 1. 1, 1 gives us a 0. 1 or 0 gives you a 0. So we have a 0 going down here and a 0 here. 0 carry, 0, 0 on this will make it a 1. And there you go. 1 add 0 gives you 1 carry 0. So if we're doing binary addition, that's what we're getting if we did this twice. So why don't we do one more? And we're going to do this time let's do carry sum. So if we did 1 add 1, so 1 add 1, normally that will give you 0 carry the 1. So let's try that out here. We've got 1, we've got 1. Let me just go to this, didn't you? Trace it through. This 1 goes down here. This one's here. 1, 1 is 0, 0, 0, 0, 0 gives you 1. So we have a 1 here, and we have a 1 here. 1, 0 here gives you 0. So that's a 0 carried a 1. So that's how this half adder works. But a half adder could also be given to you looking slightly different to what I'm giving you right here. This is another representation of a half adder. This is probably more common than what we saw a second ago, where you've got a XOR gate and an AND gate. Basically, this is the same as this circuit above. It's just simplified. So how does this circuit actually work? Well, we've got the sum at the top this time, and the carry here. The sum is linked to the XOR gate, the carry is linked to the AND gate. So if we were to do 0, 0, 0, 0 on an AND gate will give you 0. 0 XOR 0 is 0. Happy days. That is true. 0 add 0 is 0. Let's try 1, 0. So we've got the 0 here, we've got the 1 here. 1 add 0 gives you 0. 1 XOR 0 gives you 1. So that is true. 1 add 0 gives you 1. If we were to do 1 add 1, so we've got 1, 1, 1, 1. 1 add 1 gives you 1, so that's a carry. 1 XOR 1 gives you 0. 0 carry 1. So again, this is a half adder. What a half adder cannot do though is it cannot deal if we were to having to do a situation like this. Let me just clear this all up. And let me get rid of this. There we go. Let's imagine that we had 1 add 1. So let's do that, and we have 0, 1, 1. Cool. 1 add 1 gives you 0 carry over 1. For this sum, how many inputs are we going to need this time? We're going to need 3 inputs. But notice a half adder doesn't actually give us 3 inputs. It only has 2 inputs, A and B, i.e. A and B, A and B. But it doesn't have an opportunity for us to do C. So a half adder, its purpose is for binary addition. Great. But its limitation is that it cannot take into account a carry from a previous sum. So it can't take into account, in all honesty, this situation here. It can't take into account the carry from the result of this one. So therefore the half adder is useless for when it comes to dealing with a carry from a previous sum. It's great if we're dealing with single digits, so if we're just doing 1 add 0, half adder is perfect. But it's not good if we're having to do something where it's involving a carry. That's when the full adder comes into it. So picture this. We've got 1, 1, 0. In fact, let's put 0. I'm going to do 0, 1, 1, 1. So we've got in this situation 1. Actually, sorry, 0. 1. So that's 0, that's 1. And we've got no carry. It's empty. R is representing carry, and it's the same every time we do a full adder. What next? Well, let's trace it through. This 0 travels all the way down here, and we've got a 0 waiting here. We've got a 1, which will be here. We've got a 0, which comes down here. 1 and 0 gives you 0. Fine. We've also got the 1, which goes here, and we've got the 0, which goes here. 1 XOR 0 gives you 1. This 0 also travels down here and up here. 1 XOR 0 gives you 1. Notice that we've got this 1 down here. So from the result of this, so 1 and 0 gives you 0. So 0 or 0 gives you 0. So x is going to be a 1. And in this situation, our carry is 0. So I don't actually need to do a carry 0. I don't know why I did that. That was just me being tired. Now let's do 1 add 1. Nice and simple. Let's tidy this up. One, 1, and we still have 0 from the carry. There's nothing which was carried over. So we're now doing this one, 1 add 1. So we're going to have a 1 which travels here, we're going to have a 1 which travels here, we're going to have a 1 which travels down here, we're going to have a 1 which travels here, we're going to have a 0 which travels here, we're going to have a 0 which travels here. So let's work these out. 1 XOR 1 gives you 0, and 0 pops down here as well. 1 and 1 gives you 1. 0 and 0 gives you 0. 1 or 0 gives you 1. That is our carry. 0 XOR 0 gives you 0. 1 and 1 gives you 0. That's what we worked out here. Carry for 1. Which is exactly what we've got. Now, we're going to be doing 1 add 1 add 1. So let's just wipe the slate clean. So this time, this is now going to be 1 because it's allowing for the carry. So let's do it. 1 here, 1 here, 1 here, 1 here, and 1 here. 1 or 1 gives you 0. So we're going to put a 0 here, and we're going to put a 0 here. This 1 travels up here, so there we go. 1 add 1 gives you 1. Okay. 1 and 0 gives you 0, but this is going to be a 1 overall, so our carry is a 1 again. So 1 add 1 add 1 will give us a carry of a 1. That's what it's telling us here. 1 or 0 also gives us a 1, so our sum is 1. So that is correct. 1 add 1 add 1 gives you 1, carry to 1. So our final bit is going to be 0, 0, but our carry of a 1. Our carry 1 goes here, and it also goes here. Our 0 goes here, and also here. Our 0 goes here, and also here. 0 and 0 gives you 0. 0 or 0 gives you 0. 1 or 0 gives you 1. 1 and 0 gives you 0, 0 or 0 gives you 0. So, ladies and gentlemen, we are left with 1 and no carry. And there you go, 0 add 0, 1 is 1. And that is a full adder. A full adder allows us to have a carry in. R is representing our carry in. Y is our carry out, like we had last time for the half adder. So normally you would have, again, multiple adders connected to each other, rather than doing it what I just did, which is wiping things clean. Point being, there you go. Happy days. Half adder, full adder. Full adder, used together, multiple, to add multiple binary numbers.